I'm glad to introduce Alexander. He is from one of our sponsors, Robotics, and as I promised, he will talk about computer vision from basics to the some level. And please feel free to ask him any question you want, because you have actually had problem to detect and hook the duck. So you're welcome.
So good morning, guys. Let me introduce myself a little bit. My name is Alexander Rybnikov. So now I'm working in Robotics company. But before, to let you some notion, I was working at JASS. It's a company who developed OpenCV, who brought OpenCV to a level we know it. And later I also worked at Intel on some functionality for OpenCV. So maybe I have some to say about OpenCV, I hope. So if you want to see these slides on your device, you're welcome. Please scan this QR code and you can see this. So what we're going to talk about today. I'm going to tell you some basic things about OpenCV and from basics to some advanced stuff. It would be a more practical, rather theoretical thing. So it will be a bunch of code and samples, of course. And as we know, we are going to solve our task. We are going to detect and grab the duck. So it will be about this problem. Few words about how OpenCV is organized. Maybe some things will be obvious for you, but I hope you will learn something. So OpenCV includes two main repositories. It's OpenCV and OpenCV Contrib. OpenCV contains some stable and good developed models, good developed functionality. And OpenCV Contrib is more experimental things, things which are developing and maybe unstable, maybe may have some errors. But sometimes OpenCV Contrib contains something interesting. Each repository consists of modules. Module is some part of the code which implements some functionality about computer vision, some computer vision problem. And of course there are some basic modules like core and other things. So these basic models include some core functionality to glue together all models. Also another QR code. If you want to have an access to a repository with the code, you can do it right now, or can type this simple link without error. GitHub without error. So let's get started. To use OpenCV in Python, firstly we should import CV2. It's a basic thing, and we can check a version of OpenCV. It may be important because not all versions have the same interface and the same functionality, so maybe the latest version is better, but not always. In computer vision, we work with images, so we need ways to load images, to grab, to get. One way is to load image from file. It's simple function cv2.imread. It takes path to the file, to the image file, and also the mode of reading the image. If the image can be loaded as color or grayscale. We talk later about what does it mean color and grayscale. Also, we can load and read video files with CV2 video capture. It may require to install you some codecs or something like this, so be prepared. But it's not hard. All problems can be solved. Also, we can grab files from the camera. Just pass number of device of your image device instead of path to the file. And we can simply grab frames from the camera. Also, not all cameras are supported, but some widely spread cameras, frames from them can be grabbed like this. Second step, and it's also important, but okay, it's basic thing. We need to display our image. We can do it with CV2 imshow. But it's not enough to call CV imshow. Also, we need to get our system, to give our system some time to display the actual image. So we need to call the function CV2 wait key. Wait key means wait some key to be pressed. And the image in the first sample will be showed until you pressed any button. And also we sometimes need to close and destroy some image, some window with destroy window. Also, it's possible to display the image for some time, for some predefined time. The second sample does this. We display our image for 5 seconds, and if no key has been pressed, the window disappeared. Another sample about displaying images, in this case actually displaying frames from the video. So we can, wait key actually returns the code of a button. So we can react to this button properly. For example, in this sample we exit on the E key pressed. Another basic but also important thing, sometimes, actually quite a lot of times, we want to display something. We want to not to display simple image, but also to show some regions, some features, other things. We can do it with basic drawing functions, like circle, line, or rectangle. For example, CV2 line takes color to where to draw, point, start point, end point, and color, and also thickness and other parameters, but they are not very important. As you can see, we pass as a color we pass to 255 as the last value, but the line is red. So this is the reason I think maybe you know. Images, for some historical reasons, are read and loaded in BGR order of channels.
One question. Am I right that image color is a return here?
Yes.
Why?
Actually, the new image was returned. A new image with drawn lines or drawn something.
Like
Yeah. So this image.
Parameter is the original image. The parameter image color is the original image.
Yeah. Original image, and in this line I want to store my to spoil actually my image, original image, and save.
What's the last parameter again?
The last parameter is the thickness of the line. You can find all this information in the OpenCV documentation. It's very well written, I think you know, and OpenCV team does a lot of work to have a good documentation. So we can draw something, and also we can save something. We can use CV2 in write to simply save our image. We pass the path to the file with some extension PNG for this, and our image, which we want to save. Let's talk about how images are represented in the Python code, and actually in OpenCV. OpenCV in Python uses numpy arrays to represent images. It's better to talk about images not as a matrices, but rather about tensors. What does it mean? Tensor has matrix has two dimensions, rows and columns, or width and height. But tensor have 3 or more dimensions. And if you load color images, you actually work with 3-dimensional tensors. Like axis 0 is a number of rows. It's also a height parameter. Axis 1 is a number of columns. It's a width parameter. And axis 2, it's a number of channels. For grayscale images, we have this situation. We have one channel, and it's simply a 2-dimensional matrix. But for color images, we have 3rd dimension. It's important to remember about it, and also it's important to know what's the order of the dimensions. As you can see in the sample, I print shape of our images. Shape, it's a description of dimensions. And you can see first output is has 3 as the last number. This means 3 channels, B, G, and R in our case. And grayscale image doesn't have, because it's only one channel. How to access pixels and other things with numpy. We can directly access any value, like we want to set our central pixel to the green. As you can see, we have succeeded. Also, we can access to pixels as in some loops, for loop. And you can see that we access not the single value, but the three values, all 3 channels. Like we specify a place in the special dimension and get access to all 3 channels. So we can set all 3 channels. In the second sample, we set to the green some part of our image, top left corner. Also, there are some other things are available. If we want to set some part of the image to have, so if we want all channels have the same value, we can just set it. Like first line contains this sample, and we can specify from the start point to the end point dimension in this dimension. So, for example, first line we are starting from 10th. We are starting from 10th row to until the 90 row, and also for the 10th column until the 90 column. So we set this rectangle square to the black. Also, it's possible to say I want all the values be along some dimension set to some value. The second line does exactly this. So we specify only rows numbers, but for column numbers we say do it for all columns. And we see black line. Also we can have an access to the whole channels. In this sample we display B channel for our image. As you can see, blue rectangle became white because it has 255 value for blue channel. Let's talk about some other useful things with NumPy. If we want to copy image, we need to. It's not enough to simply say image 1 equals image 2. In this case, if we start to change image 1, we actually changing image 2 because it's not. I think you know this thing in the Python. We interact with objects by references, not by values, and copy them also. Makes your code faster because you don't need to copy the whole memory, but also it can give you some troubles when you want to actually change our image, but starting to change the original one. So to copy, there is an np copy function. Also, sometimes we need to create new matrices, like we don't want to load this, but we want to create something by ourselves. We can do it with zeros and ones function. Also, we can use np full function. All these functions, they are similar, and the first parameter is a shape. It's what we want our tensor to be. Like for first example, we pass 100, 103 as our shape. What does it mean? It means that we want our tensor to have 100 rows, 100 columns, and 3 channels, if we want to interpret this as an image. Also, some simple multiplication, dividings by value are available. Also, if we want to pad our image with some border, we can do it also easily with np pad. Also, we can easily save our image, our tensor. It's something different comparing to imWrite function, CV imWrite function, because np save saves our tensor. It supports multi-dimensional tensors, and it's cross-platform. You can save in some operation system and load it in another. Also, you can easily load this back with np load, and this simple sample shows how you can compare two arrays, two tensors, if they are equal or not. Also, sometimes we need to combine few images to one big image for display purposes, for many things, for saving purposes. We can do it with H stack, which translates horizontal stack. We can do many images in horizontal. And also V stack. And another useful thing is np pi. We can.
Why is that useful?
Because you don't need to type in yourself all the numbers of pi. You can just call np pi.
Python? Actually, I have one question about resolution. So when you take the picture from a camera, do you get camera parameters Or what's the default resolution for the picture?
Yes, yes, you.
1024, I think, but there's different powers. Are you able? Is there metadata about the picture? that you can access?
Some data is available about imager device. OpenCV allows to get some parameters of the camera, but not all. And if you simply take an image, it returns you the full resolution of the imager.
But you don't know, or can you get it?
Yes, you can get it. Then you call dot shape of the image. It gives you exactly the shape of the image, like 1024, 768, and other things. Now we are ready to talk about some more advanced stuff. And let's start with color conversion. As I said, images are loaded in BGR format, but OpenCV allows to convert this image to our color formats, like we can swap B and R channels with CVT color function, with parameter color BGR to RGB. Also, many other color spaces are available. For example, HSV color space, and we can convert it to grayscale to merge all channels and have only intensity information. And let's also, it's possible to convert images from uint type to float type. What does it mean? As you know, pixels in the image stored in the disk are in range 0 to 155, and it's sometimes, and this is a uint8 format. It's an integer type, but sometimes we need to work with floating point numbers. And we can convert these numbers with tensors with numpy function as type. We just take our original tensor and call function as type and pass the type we want our tensor to be. So let's convert our image, our uint8 image to the float and display it. As you can see, the left window is empty. It's kind of empty. It's because in the first show, we tried to display the image, float point image in range 0 to 155. And OpenCV thinks, okay, it's a float point image, and I think floating point should be from 0 to 1. And all things larger than 1, they are considered as white. And but second show, we display the image which was divided by 255 to normalize, to have a 0-1 range. And we have our image, but in strange colors. Again, OpenCV expects image in BGR format. And in this image, we swapped R and B format, R and B channels, and that's why we have blue image instead of red. Let's talk about color filtering. We can detect objects by knowing its color, its range for colors for our object. But RGB color space is not the best for these things because intensity information is mixed with color information. But for our purposes, we want to set color and say, oh, okay, this is my color, and I want to see all its intensities. I want to find objects with full range of intensities or larger range of intensities. So we can convert our image to HSV format and set lower and dark yellow and light yellow borders and call CV2 in range function. This function returns, accepts of course our image and border values and returns mask. Mask is a single channel image where 0 elements means the pixel doesn't have value in our range, and white pixel means the value was in range. And when we simply take our original image, copy it, and set all the pixels which are black to the black. So to have only our selected parts of the image. And we can see the result. So almost all duck was selected by our filter. And another example, it's more interesting, not because of huge duck, but because of we have some other yellow things instead of our duck. And also our duck has some holes, because not all colors of the duck were in range, were in our...
Question, can you do a 3D picture of the duck? 3D picture with the OpenCV methods?
Yeah, there are functionality which helps you to retrieve 3D information from the texture, but a duck is not the best sample for this thing, because...
Well, we're dealing with ducks here, so that's why I'm asking, but any 3D, was it 2.5D, or how far can you get 3-dimensional here?
I will cover some parts of your question later. But if you want to retrieve exact 3D information from the images, you need to work with textured objects or use our methods which helps you to retrieve this information. So we have in this image we have two types of problems. Yellow regions outside the duck and black regions inside the duck. So we can address these problems with morphology operations. To remove, there is a morphology operation called opening, and it allows you to remove some small regions. And also there is a morphology operation closing. It helps you to remove these black holes inside our object, inside our mask. So let's apply them and see what we can get. Yes, we removed these small yellow regions, and also we closed our holes.
One question. How to control the size of removing objects?
Yeah, we can control it with last parameter of kernels. As you can see, first two lines, it's a get structuring element. It's a function which returns your morphology kernel, and the size is the last parameter. We can make it bigger, we can make it smaller. For example, for closing operation, for opening operation, we say that we want to remove objects smaller than 10 by 10 pixels, or 10 in one dimension. And for close operation, we want to remove holes less than 50 by 50. Another interesting thing, when we get our region, get the duck, detect it with color filter, we want to know its borders. So in this image we have only bunch of pixels which we are preserved, but we want to get a shape of this area. We can do it with find contours function. Find contours works with binarized images. What does it mean? It means that all 0 pixels are considered as 0, all non-zero pixels are considered as ones. And find contours tries to find closed lines on our image. So we can just pass our color image to the find contours. It returns something we are not want it to return, and we need to somehow binarize our image. Let's watch to our sample. We call find the contours with some parameters. First, we pass our mask. Second, it's a mode for find contours finding, and the last parameter is how to merge points of the contour. For example, this chain approx simple allows you to merge some points on lines to just start and end points, not to have all points in the middle. Just to some optimization purposes. This function returns our original image, also contours, and the hierarchy of our contours. Now I'm going to explain what does it mean. Contours, each contour is a set of points. Our contours returned each list of these contours. So actually it's a list of points. And hierarchy.
Would the contour be aligned? Or it's
no, it should be closed. Should be closed. And hierarchy, it's about how our contours are organized. For example, we want to find contours for this image, and also we want to find the contour for dark eye. It's possible to do with this functionality. And we are going to use some prior information. For example, we know that the contour for duck is the biggest contour on the image. And also we know that the contour for eye is nested inside the contour of the duck. And inside the contour of eye, there is no any other contours.
Can you also find the contour for the wing? Or is there a couple of contours?
For the wing?
The wing.
It's possible to do with our, it's possible, but as I said, we need to pass binarized image. There is, find contours works with binarized image. And there is some other function, CV2 Kenny. It's an edge detector. It can find all the edges in the image and returns this binarized image, where all points on the edges, they are marked as white, and other points are marked as 0. So we use this prior information for our purposes. We in the second line we chose contour with maximal perimeter. CV2. It may be a little bit complicated, but I hope for you it's not complicated at all.
One is a duck.
Yeah. We just took the contour with max perimeter and said it's a duck contour. And also then we are going to revise our hierarchy contours and find contour which nested in our duck contour, and also doesn't include any other contours inside yourself.
Actually, I don't understand. What is squeeze? So you flatten this and find the
Squeeze, it's another useful function for NumPy. It helps you to remove single dimensions. For example, our tensor may be 1 and 100 by 100. So actually, we first two dimensions that doesn't contain any information, and we sometimes want to remove them. And p-squeeze helps you to do it. So hierarchy, it's another list, and its length is the same as the contour's length. So for each contour, we have entry in the hierarchy. And each entry in hierarchy contains 4 elements. So first 2 elements are indexes for next contour in the same hierarchy level and previous contour in the same hierarchy level. And in this case, we use other 2. Third element, it's information about index for contour is nested inside this contour. And fourth element, it's information about parent contour. So it's about which contour surrounds our contour. It may be a little bit complicated, but if you go to a repository and play with code, you can take a notion about how it works. And let's display our found contours. It can be done easily with draw contours function from OpenCV. And yes, we have succeeded.
Is it possible to have contours which are intersect each other? So if I have some kind of, I don't know, edge or something, could contours be intersect or not?
I think no. No.
See, actually the wing is touching the outer contour. The wing could even go a little bit. If it's a good long wing, it could actually go beyond the body.
It could be
But it would not be
two shapes.
It would be actually still the contour of the duck, right?
So if we have a long wing which is out of the duck body, will we have 2 parts of?
We will have 2 touching contours. One for the whole duck, the whole perimeter of the duck, and another for the wing. Yeah, nested inside. We will be touching something like
So
here.
an oval, but the duck would still have an extension on the body.
Yeah.
Okay.
When you're just taking binary images, the wing will just be white. Therefore, it won't be detectable at all.
Yeah, for now it's not detectable. But as I said, there is a canny function. It's a canny edge detector. It helps you to track all the points on the border. So if we have even small gradient, we can retrieve information about the border with canny function. I don't have an example, but you can find it easily.
There are examples on canny detector.
Yeah, OpenCV contains a lot of this information, and also it's easy to use. So let's talk about 3D and how we can get 3D information from 2D image. First step is we need to know parameters of the camera. Why it's important? Our camera takes images and actually it takes projections from 3D stem to the imager. And there is some math connected to this projection. For example, we need to know how our camera is projecting 3D objects into sensor. So we need to know how actual size of a 3D object translates to the pixel size of the image. This is one part of our camera parameters. Another part is how our camera spoils the image. it actually distorts the image, and you can see it especially for fisheye lenses like GoPro and other things. You can see that straight lines, actual straight lines, are not straight at all on the GoPro cameras. And this effect should be eliminated to properly work with actual 3D geometry of the objects, because we need lines to be lines, not curves. These are about distortion parameters. Here I have some sample images. You can see that there is an ideal image without distortions, and camera actually distorts our image. Due to the shape of the lens or some imperfections, it spoils our image. And the far away from the center of the image, actually from the center of the lens, the worse the picture. As you can see, in the center we have almost straight lines, but around the edges we have curves. And also it's important to say, as you can see, 3D blue arrow projected to the image, small blue arrow on the imager. But actually this arrow can be in any position from the imager to the actual 3D arrow. So it's important to say that our imager kind of eliminates the z coordinate, and just allows us to know the direction from the camera, where the object was, instead of its actual position. Later I will tell you how to retrieve, or how to try to retrieve actual position for the object.
In the matrix up there, the R11 T3, what is that?
Yes. In the projective geometry, we are working with homogeneous coordinates. It's an expression of idea that our object can be anywhere, but it projects to the same pixels. Like a blue arrow can be anywhere in this red ray. And first we have some object, usually idea of object usually is connected with the local coordinate system of the object. So it's convenient to set coordinates of the object in its local coordinate system. For example, if it's sphere, it's convenient to place start of the coordinate system in the center of the sphere. But our camera and our object are somehow placed in the 3D scene, and they have some relative position, camera and object. And we need to go from the local system of the object to the 3D, to the local system of the camera. And the first matrix does this. It includes a rotation matrix and translation vector. And by adding one to the actual position of our object, it's easy to work with translation as a multiplication operation, like matrices operation. And there is another matrix. It's matrix about camera parameters. It's how our 3D point, when we moved to coordinate system of the camera, it's how this point is projected to the image, to the pixels. It contains focal length in the diagonal, and also a center point. You can see it on the image. So
looking for R's and T's, but
center point, it's a principal point. It's axis of our lens system. And
the R's and the T's, what are these?
These are how our local coordinate system is connected with object's local coordinate system. So how to move from object local system to the camera local system. It's about transition between coordinate systems.
So is that a constant matrix for each camera? different, but
It's actually it depends on the actual object position. So if we have camera fixed somewhere in the world and move the object, because we move a local system of the object, we change these metrics. And also, if we have object fixed and move the camera, also relative position from local system to the camera system is changing. And
you said all this during calibration.
During calibration, we get actually aim of calibration is to get first metrics and also distortion coefficients. But we can know actual rotation and translation for the object later. So as I said, what we need to find during calibration? It's a parameter of projection, how 3D points project with 2D, and also how the image is spoiled by camera. It's a distortion coefficients. And the main idea is to
The projection will be different according to camera and lighting, right?
No, it depends only on camera parameters. It's called camera metrics. It's called also intrinsic camera parameters. It's connected with lenses of the camera. With no, lighting doesn't influence these things. It depends on the focal length or lenses or.
How can you get these parameters? I mean, they're static, right? So with every camera, there are these parameters, and they don't change.
If we have some camera, it has some intrinsic parameters. Yes, they are fixed. We need to do calibration once if we are not changing its internal parameters.
Take a GoPro. What do we get out of a GoPro in terms of parameters? What can we get?
We can get first metrics,
okay,
and also distortion coefficients. So we will be able to turn this image into this image and know how to points are projected.
Are there any OpenCV calls that you have?
Yeah, it's.
How do they look like?
I will cover it a little bit later. So.
Can you go one slide back?
Mm-hmm.
So what you practically do when you calibrate the camera is you put like a test image.
Mm-hmm. I will tell you about this. 1 second. So we need to find, as I said, intrinsic camera parameters and also distortion coefficients of the lenses. And the main idea is we can take some object with well-known geometry. Take a lot of photos of this, and because the object was the same, we can solve optimization problem. How to find these camera metrics and distortion coefficients to have the best reprojection for all our photos. This is exactly steps we need to do. Firstly, we need to prepare a calibration pattern. OpenCV supports a lot of calibration patterns, and they are something like this. It's actually planar object with known geometry, and it's very important for object to preserve its geometry. It's not enough to just print this sheet of paper and trying to show it to a camera. It's very flimsy, and it will influence our calibration process. So we need to better glue it to, or attach it to some rigid and flat surface to preserve its geometry. Also, it's important to say about zoom lenses. If we have some lenses with zoom, this zoom actually influence coefficients fx and fy. So if we change the zoom, we change the camera metrics. It's very important to know, because you may calibrate for one zoom and try to use with another zoom, and there is an error. Our lenses are projected with an error.
Does it mean that we have some function for each value of zoom?
Yes.
If we need to work with camera with zoom, we should create 3D model of
Actually, yes.
of distortion.
Yes. So we need to find all the full zooms, or just fix the zoom and use some fixed parameters. Another step is take a lot of photos of our calibration pattern. So we used a camera and our good calibration pattern, and by taking a lot of photos with various angles with various positions, we can cover all the field of view camera, and it's better to cover all the field to correctly restore all the function, all distortion coefficients, all the metrics. Usually 100 frames is sufficient to the good calibration. Next, we took a lot of photos, and we need to find points of our pattern on the images. OpenCV lets you do this, and we will review it on real samples on the next slide. Next, we found all the points for our images, and we solve optimization problem to find camera metrics and distortion coefficients. And the metric is used, and it's a reprojection error. What does it mean? We found our object, we found its 3D points, and we know some parameters of the camera. Let's project these 3D points back to the image and compare projected points with the image, what we found on the image. This reprojection error, it's a mean error between these points, reprojected points, and actual points on the image. And actually, it's a tenth of a pixel, so it's very small. And if you
This earlier, let's say after 10 photos, then you could stop.
10 photos.
You said 100 photos is sufficient, but if the reprojection error is already at 0.3, why should I keep going? Or if it's not there, then maybe I need 1,000 pictures. Or is it?
Unfortunately, your reprojection error is sometimes can lie to you about a successful calibration process. Because we can, it's like a learning process. We can overfit to our small part of images. So we can do calibration actually with one frame, but it would be very worse calibration parameters because we didn't cover all the corners. We aren't able to recover actual function, distortion function for corners, but it may be important because object is not in the center of the image all the time. And there is an actual sample. As I said, we take photo. Actually, you can launch this code from the repository I mentioned. So we load image. We know the size of the pattern. What the size of the pattern is? Actually, it's internal corners. So corner is a special point which lie on between two black squares. It's not this point. It's actually inside. It's also remember. It's good to remember this thing. So actually, our pattern has more squares when we have 10 by 7 but we exactly have 10 width corners by width and 7 corners by height. So we create, we know this pattern size. OpenCV has a function find chessboard corners, which detects you, roughly detects you all the corners from the image.
Actually, I don't get it. Chessboard has 64 squares.
It's pattern, not.
Oh, chess.
No. It's not about squares.
Checkered pattern. Okay, got it. It's okay.
But in OpenCV it calls chess.
So they don't care about it.
OpenCV chess.
Yes, actually, these are not squares itself. It's intersection, kind of intersection of the squares between the squares. So we found our chessboard corners roughly, and then we can to improve our accuracy by finding with corners with subpixel accuracy. It's again solving some optimization problem. If you're interested, you can find it in OpenCV documentation and other links in the books. But actually, we need to find some better points. It's not an actual pixel position. It's subpixel position. So we can fit some lines for our corners to find its exact subpixel position. So it adds to the position of the corners floating part. Because our corner may lie inside the pixel, may lie somewhere, and we can restore its actual position. So CV2 corner subpix finds this subpix position, and when we done these things, we can display all the stuff. So I took this photo, and OpenCV helps to visualize it. As you can see, this rainbow pattern, it's what CV2 draw chessboard corners done. But also as you can see in the code, also I displayed all our raw corners from the find chessboard corners function. And you can see with raw corner and with subpixel corners. They are not, sometimes they are not in the center, so it helps actually to improve the accuracy. And the final step, we need to solve optimization problem. It can be done with CV2 calibrate camera. It take all these parameters, our list of our points for all images, list of our found corners. So actually as you can see, first 2 lines are about 3D object points. What does it mean? We set these points in the local object's local coordinate system. And it's easy to say I'm trying to say that because the camera does not can't recover actual position of our 3D object, we can move it closer to the camera and have a smaller pattern, or we can make it bigger and place it further, and we can have the same image for both scenarios. And that's why it's possible to say that, for example, our square size was 1. It's some units. It's and due to the projection geometry, it's unimportant what's the actual size for now, because we have the same pattern, and we actually don't need to know the exact distance from the points. And we can use this information to simply turn corners indexes to corners coordinates. for example, second corner has one index and its point is 1, 0, and first two rows do exactly this thing. CV2 calibrate cameras take these points, 3D points in the local object's local coordinate system, takes corners we found on the images, also image shape, and some another two parameters which are here because of some not very ideal Python wrapper for C++ code, so that doesn't matter. And it returns this reprojection error, root mean squared error, camera matrix. It's a 3x3 matrix. Actually, this matrix. Oh. Also, it returns distortion coefficients. It's a vector of coefficients, how our distortions, our lens distort image, and list of rotation vectors and translation vectors for each pattern. So our image, because we said that our square size is 1, our function can restore actual 3D position and rotation, how it was placed in front of the camera.
So if I'm programmer, I just have to call calibrate camera with those parameters.
Yes, but
then I would like to know what is reshape. Maybe
with
the first reshape, T dot reshape.
Second line.
What is that?
it's just preparing our. So we want to create 3D points for our object in its local coordinate system, and it's just the easiest way to do this. So we need to turn our points to the indexes, and then consider these indexes as two-dimensional array. So as I said, it's not important to know the actual geometrical size of the side of a square. We just need to say it's, for example, would be one in some units, and because we can move it.
So you normalize basically. Normalize short or long distance to a specific.
No. It's not about normalization.
Or maybe I don't know what that's up. I don't understand, but I guess maybe the others understand.
So
that's called calibrate camera.
as I said, this arrow can be somewhere in this ray, and we can say, for example, this arrow can have size of 1, length of 1, and and imagine for now that we have, instead of this arrow, we have our calibration pattern, our checkerboard, and we say that.
Integrate that to 1.
Yes, it's.
In this plane.
For now, we don't need to restore actual position, actual geometrical position of our calibration pattern. We just want to calibrate camera parameters, and we can, for simplicity, say that this the size of a square is 1. It's possible due to it gives us the wrong translation and rotation vectors, because our real pattern doesn't have 1 length of a square. But for this function, it's not the case. We want to find camera metrics and distortion coefficients, and this one doesn't influence this matrix. So it's just for simplicity and for not to measure actual size of our calibration pattern. So when we can restore 3D information from 2D image, when we know the exact geometry of the object, so how big it is. So if we want that where our arrow has length 1, and we can restore actual geometrical position. And when we know distance for an object, it may be some simple object, planar object, actually, for example, circle, and we know that the circle has some certain diameter, and we can restore how far it was during taking photos.
One question.
Mm-hmm.
Does it mean if I have some, I don't know, red ball with no size, I can measure distance only by one camera?
Yes, yes. If you know the exact size of a ball.
Does it mean that I can mark up my 3D space by these balls and just have 3D coordinates?
Yes, you.
If I have moving camera, I can just.
Yes, it's possible, but you need to know that because the ball
Okay, so
will be small.
maybe this size or something.
If a ball is small, it has a small number of pixels in the image, and by changing it for 1 pixel, it can be a huge difference in the position.
Basketball ball.
Yes, actually you can restore actual 3D position, knowing its size.
One question.
Mm-hmm.
Regarding the calibration of the camera, you said that it's good to use multiple images.
Mm-hmm.
How does the process change with the high number of images?
It actually doesn't change. As you can see, I used here our pattern points as I turned our pattern points to a list of a pattern of points with 1 element. It's just because CV2 calibrate camera expects a list of a list of the points and list of the corners. But it doesn't actually change. You need to know you need to collect all of your pattern points as list and also as a corner points, it's also as list of list. So we can, as I said, we work in homogeneous coordinates. So we have one for z. When we are working with image points of the image, and we can restore this ray for some point on the image. And actually, that's it information. We don't have actual 3D information. We only know the ray from the camera coordinate system to the point on the image. And OpenCV has functionality to restore this ray. It can be it can also OpenCV can remove this distortion from lenses. So to have our lines back to be straight, not to be curved. This piece of code does actually this. CV undistort function helps you to remove these distortions. So this is a result for the same image, and you can see we have some curvy black regions around the image. It's due to our image was undistorted back, so squeezed or resized to have actually straight lines, straight. And CV2 and CV2 undistort function actually has some parameters to get the image without these black regions. So if you're interested, there is a documentation about this. As I said, there is a possibility to restore this ray from the camera coordinate system to the object point, actual 3D object point. And we can do this by undistorted points. Yes, the name of the function does not tell about its purpose. It's actually, yes, it's actually undistorted points from the image, but also it returns them in the homogeneous coordinates. As you can see, I printed first coordinates of the first corner, and it's in strange floating point numbers with minus signs. This means exactly what we moved from the pixels, where we have zero for coordinate system in the top left corner, to this coordinate system where we have 0 here, and all the points. So points from the left, they have a minus sign. So that's why we have these strange coordinates. What we can do with these 3D points? Actually, it's not now. It's not a 3D points. It's 2D. We can, but to turn it to 3D, we can add 1 as a third coordinate, as a z coordinate, and after this, it becomes a ray from the 0 point from camera coordinate system to the actual 3D point of the object. And actual 3D point of the object can be somewhere in this ray. We don't know actual position. And we can project back this point to the camera. We need to use project points. This function is to project 3D points back to the image. So we add 1 for each point to turn our 2D homogeneous coordinate to 3D, and call CV2 project points. It takes our 3D points, it takes our translation and rotation vectors, and also it takes camera matrix and distortion coefficients. Here I passed 0 distortion coefficients because I want to project them back to our undistorted image. We removed our distortion and we can project to our ideal image. And let's display them with the rest of the code. So yes, we have our undistorted image and have our images exactly in the corners. But it sounds like a magic. What actually project points do and does, and how it connected with these maths. The thing is, we can do all these things by our hands. What should we do? We just should multiply our corners by camera matrix, and actually how our 3D points projected back to the image. So we just multiplied them and divided by z coordinate, and just again display. Yes, this is correct. So project points does not do any magic. You can do all by your hands, except you don't need to distort points. In this case, you need to apply some distortion function. For example, we have cube, 3D cube, and we know its size. We know its geometry, and if we detect all the points of the cube, all the vertices, we can restore its actual 3D position and rotation. It can be done by CV2 solve PNP function. It takes a set of 3D points in object local coordinate system. It takes points from the image, 2D points, and also camera metrics and distortion coefficients, and returns you rotation and translation vectors, how the object is placed in front of camera. Again, returned vectors are in this local coordinate system of the camera. So another important thing about 2D to 3D, we can use some special objects which are easy to detect and easy to locate to get this information about where's position and rotation. There are these special markers. They're called Aruka markers. These are objects with this strange pattern, and they are easy to detect, and they can be information about their placement in the world, in the front of the camera, 3D placement, can be restored. OpenCV has this functionality, but it has it in contrib modules. So you need to have OpenCV with contrib modules to use this. So we just import what we need. And the thing is, OpenCV allows you not only to detect these patterns, but also to create this. If you want to print them, if you want to place them in the real world, it's possible to do this. So I just created the image of a marker with OpenCV.
To fiducial markers.
Hmm?
What's the difference? How do you say that? You call them Aruko.
Mm-hmm.
I learned them as fiducial markers. Is there a difference?
I haven't heard. Sorry about.
I'm just older.
Mm.
No, 30 years ago, these were fiducial.
Maybe they're about the same idea.
There might be a difference. Yeah, these are all squares,
Mm-hmm.
but not rectangles. Or
Yeah. These are exactly squares. Yeah.
They're always squares.
Yeah. They're always.
They're always the same size.
Mm-hmm. Yeah.
And then it's a subclass.
Mm-hmm.
Okay.
So we know for Aruka marker, we know its ID.
Is that an acronym?
Aruka, yes. It's Augmented Reality University of Cordoba. It's created by Spanish guys. So we know exact length, actual 3D length, actual object length of the side of the marker, and because due to it has this special structure, we can easily find these markers around us by camera. So we can do it easily. So here I load some photo with Aruka marker and create detection parameters of this. Mm-hmm.
Is it possible to put any information to the Aruka marker?
You can do it by
What's the difference between workflows?
Aruka marker actually has one single identifier. It can be restored. This identifier, it's an integer number.
What the identifier space from 0 to what?
It depends on your dictionary. It's called here dictionary.
Oh, okay.
So it's how these black and white squares are translated to this ID. Of course, it has some redundancy, some extra information.
Sounds like it's just a number.
Yeah. It's just a number.
How big is the predefined dictionary?
There are different dictionaries. Here we have 1,000 markers.
1,000.
Yeah.
And for Ducky Town, what do you have?
I don't know.
But OpenCV has.
Create more, right?
Yes,
We
sure.
can print them
Yeah.
also. Like airport, with the two airport markers. Okay.
Just a number. How many objects?
Well, 50,000.
Can we store arbitrary data on these codes?
So we can connect our arbitrary data with this identifier.
Okay.
So it's it's like a key in a map.
It probably has some value. It must be easily identifiable, right?
Yeah.
Even with a low resolution camera, that's why.
Yeah. The main purpose is,
You cannot do arbitrary.
yeah, it's not like QR code when we can store.
The parameters from the draw marker. So the first of them is obviously the dictionary.
Yeah, yeah.
The second is
The second is ID of the marker.
So this marker has ID for.
Yeah, yeah, yeah,
Okay,
yeah.
And I decide the ID however I want.
Therefore, something good quality over there.
Yeah, yeah. You can choose any ID from dictionary from 0 to 1000.
And the third is just data.
Third, it's a size in pixels of a marker. Yeah.
Okay.
So we can detect these markers on our photos, and it works decently fast in OpenCV. So we detected this marker on our photo and draw our borders. OpenCV has all this functionality. So we have aruka.detect markers and aruka.draw detected markers. So it's easy.
One question. You said that this is available in country repository,
Yeah.
right? Is it available for ARM platform or?
I think yes. OpenCV also builds its code for many platforms, not only Linux, Windows,
iOS.
iOS also, yeah, Android and ARM, yeah, and some NVIDIA devices, Tegra.
Is it possible to just install OpenCV to Android phone from the market?
Very.
Or you have to build it for Android?
Yeah, there was OpenCV in Play Market for Android, but I don't know, maybe it's not supported longer, but you can, with instructions, you can build your package and install. It's possible. So we can not only detect this aruka marker, but we can restore its rotation and translation positions. If we know its length of its side. So here we have estimate pose single markers function, and we pass the corners of our marker and also exact position in some units. In this case, it's a position, it's a length of our marker. Sorry, actual length in meters. In meters. I had small aruka marker, about 8 centimeters. So I just passed this. So here, this is very important to know exact length, because if you say that your marker was bigger, it should be further from the camera to have the same projection to our image. So we can estimate its pose, and also because we estimated its pose, we can draw its coordinate system. And again, we can do it with OpenCV.
So does it mean that if I rotate this somehow, it also be detected?
Yeah, it's also be detected, and with 3 axes, we rotate it and place it correctly.
So it means I can change my bolts to the aruka marker?
Yeah. Actually, if you want to have decent accuracy, it's better to use aruka markers as your special objects. It gives you a very, very good accuracy, and it's easy to detect. No false positives, so it's specially constructed and good objects. So let's talk a little bit about my ideas to your problem. So firstly, we need to detect the DAC. And we, as I said, we can use color filter for this. Next idea, we can take the contour of the DAC, and if we know the size of the DAC, actual size, or some estimate of the size, because we can measure it with a ruler, we can estimate how far it was by solving the proportion. Its pixel size and its to its actual size, and we can get Z coordinate. Of course, this proportion is not very simple, as I said, because you need to go to the homogeneous coordinates, find this ray, and also find proportion for the ray, not for. It can be not the duct can maybe not in the center of the image, but in the around the corner. So you need to correctly solve this ray and 3D geometry, but it's not very complicated. Another idea, you can take these special structures, like we can have a lot of Aruka markers and place our duct inside the Aruka marker. So surround our duct with Aruka markers. It gives us the exact region where to detect duct, and it gives us exact how far we from the surface where the duct stands. Now I think that's it about some code and some samples. Now you can relax, and I'm going to tell you about some other useful things, but it's more words than code. I think there is no any line code further. So there is a deep learning in OpenCV. So you can there is a special module which supports loading pre-trained models from CAFE, TensorFlow, and Torch, and you can launch in OpenCV. You don't need GPU, you don't need anything, you just need OpenCV. And this model, this DNN model, so this portion of this functionality was added by me. So have fun.
What about performance?
Performance is one, but I was thinking, could you not do the calibration of the camera even with deep learning?
Calibration.
Yeah, well, you just show the pattern, rotate it, you translate it.
So actually there are some auto calibration system, because we can find some key points in the image, and because the image is changing, if it's dynamical scene, we can compare with if we have a good way to compare these key points to have exact matches. We can see how images are changing if our object.
Do that with supervised learning.
No, it's structured for motion. It's just tracking distances between key points.
I'm just worried about this 100 times of taking a picture here. And I'm not even sure the 100 is arbitrary, or I mean, you still have to do this 0.3 edge detection. I don't know what was that? You went it down to sub-pixel value, right? To get the match when you calibrate the camera.
Mm-hmm.
I feel it's much nicer if you just wiggle a little bit with the chessboard.
Yes, you need to.
This is it.
Maybe it's a good topic to research, I think. So this model has a lot of samples. You can easily just download and run classification, segmentation, object detection, face detection, and others. So you can easily, on your CPU, on your laptop, or on almost any device, you can launch.
You can also say hello, comma. Is that another device, or Raspberry Pi understand mobile devices? Hello.
Yeah.
Who is hello? GPU isn't used.
So I mean that you don't need to have powerful GPU devices to launch your models. So you can, it's possible, and there are projects you can build OpenCV with DNN model for Raspberry Pi and launch your models on Raspberry Pi, and it works not very fast because Raspberry Pi.
Actually, Raspberry Pi has GPU, but yeah, no power.
And there is some work to enable these GPUs in this DNN module, transparently enable, without installing any special drivers or something CUDA, without these things. So it's called Halide language. So it's not a full Turing language, but it helps you to optimally, very fastly write kernels for these layers. So it's possible to enable GPUs. And it's worth to remember this model is fresh, new, and it's still developing. So, and I hope tomorrow it will be better than today. So it's better to check out the latest version.
Have you had a special contribute?
So I added TensorFlow Torch, support for TensorFlow Torch models. Also enabled some testing system to continuously check that all is correct with all the things. Also, I compared how good these models work inside the inner model. So in terms of accuracy of metrics of a model, not performance and numbers and something like this. Actually in accuracy, like classification accuracy, like segmentation, object detection. I think that's it. Also about some my ideas about Python tools. I use PyCharm in my work, and it's a really good environment, I think you know. And also I use Jupyter notebook if I need to fastly prototype something. It's also very convenient and it can be launched. It's easy to save some image data, some graphics, some output inside this notebook, and you can share it. Books. So my favorite books about OpenCV is Learning OpenCV Free by Gary Bretsky and Adrian Kehler. These are two guys. They are actually creators of OpenCV. So, and they know a lot about OpenCV. And advertisement, a little bit of advertisement. So I have my own book about OpenCV. Unfortunately, it is not, you can't buy for now, right now, but it's coming soon. Like I hope.
Did you bring a copy?
I have not received my copy yet, but it's a matter of time.
Okay.
So it's a little bit of advertisement. So useful links. OpenCV has a special page about books, and you can find this book from Adrian Kehler and Gary Bretsky there, and also other books, other useful books. Also OpenCV documentation, but I think if you Google something, you find it easily. And OpenCV GitHub, and I want to say that if you have any issue, if you have any question, it's better to search inside issues in OpenCV repository. Because sometimes it's very useful information in comments from contributors, from developers about functionality. And if you need to understand a deeper understanding of something or how to solve some issue, it's better to also revise issues, even closed issues. So it may be useful. So it's again link for this presentation. And any questions do you have? So yeah, maybe you still have. And that's it. Thank you for your attention.
Actually, I have one question. No, last one. Will you stay around and help out here? Are you just a speaker, or will you also be a co-developer? What's your role here?
What's my role here in JASS? Or in so I can be as a consultant. I can give you some.
So the question is, we have a Slack for everybody,
Yes.
and we can create a channel. And if you have some time, we can add you.
Yes, yes, I can help you. Yeah.
The 24-hour help desk would be
Not 24.
24, but with 5-hour delays.
yeah, that would be helpful.
Yes. So, and I highly recommend you to download all the code from the repository. It has not only the code, but also the data. You can run all code and see what's changing if you tune parameters or do something. So it's better to get your things dirty with OpenCV. And without this, you don't fully understand how it works. Yes.
Actually, link is already distributed via Slack.
Okay.
Thank you.
Yeah, thanks again.
Maybe can you provide the link to nightly builds? I worked with OpenCV in my Android device, and I don't remember, but I had some problems with it, and I got a link to the nightly builds, and this problem there was
Disappear.
yes.
So you wanted to say that you downloaded the nightly build
Yeah.
and all was fine?
Yes.
Maybe actually I don't have any experience with Android and OpenCV because my interest was something elsewhere. But I think we can solve this problem if you just ask in this Slack, or just I think we can Google something and find solution. Yeah, or we can directly ask questions. We can, if you have any issue with OpenCV, you can raise an issue in GitHub. So, and guys from OpenCV, my ex-teammates, will answer you.
Thank you again.